Hello everyone, welcome back to my YouTube channel Physics Unification. In this video, we can discuss the 3 marks and 5 marks derivations from the chapter Electrostatic Potential and Capacitance from the 2nd PUC Science 2nd chapter. The revision of expression for electric potential due to a point charge. Consider a point P which is at a distance of position vector r from the charge Q. Intermediate point P dash in between P and infinity. Then the electrostatic force can be written it as F is equals to 1 divided by 4 by epsilon naught Q1 Q2 divided by R square. Here only one charge is there, therefore Q1 equal to Q, Q2 equal to 1. Then electrostatic force F can be written it as 1 divided by 4 by epsilon naught Q into 1 divided by R dash whole square into R cap. Here R cap is the unit vector along O P dash, OP dash or QP dash. Now what we have to write? Work done against these force in moving charge plus 1 coulomb from R dash to R dash plus delta R dash. Can be written it as W is equals to force into displacement F into minus delta R. Here negative sign which indicates the work has been done against the force. Then which becomes value of F equal to 1 divided by 4 by epsilon naught Q into delta R dash with a negative sign divided by R dash whole square. Let us take it as equation 1. The total work done by the external force can be obtained by integrating equation 1 from R dash is equals to infinity to R dash equal to R. Then what happens? Equation 1 becomes W is equals to negative minus, just take outside, integration from infinity to R 1 divided by 4 by epsilon naught Q divided by R dash whole square into dr dash. Then which is equals to minus 1 divided by 4 by epsilon naught into Q. And we know integration of 1 divided by R dash whole square into dr is equals to minus 1 divided by R dash plus integration constant. Then substitute this value in the expression, then what we will get? Minus 1 divided by 4 by epsilon naught into Q. In place of that integration value, we have to write the minus 1 divided by R dash from infinity to R value. Then here minus, minus into minus which gives plus value. Q divided by 4 by epsilon naught, just take outside. 1 divided by R dash infinity to R. We have to substitute upper limit first and lower limit next. Q divided by 4 by epsilon naught into 1 divided by R minus 1 divided by infinity. Then work done can be written it as W is equals to 1 divided by 4 by epsilon naught into Q divided by R. That work done on unit positive charge is the electric potential at P. That W which itself gives the work done on unit positive charge Q, and itself it gives the value of electric potential at the point P. Thus, electric potential at P due to the charge Q at origin can be written it as W becomes V of R is equals to 1 divided by 4 by epsilon naught Q divided by R. As position vector increases, that value of potential, electric potential which goes on decreases, because here V is inversely proportional to the value of R. Up to here, this is for 3 marks derivation. Electric potential due to a system of charges means more than one charges. Consider a system of charges Q1, Q2, Q3, Q4, Q5, so on up to Qn with position vectors R1p, R2p, R3p, R4p, R5p, so on up to Rnp with respect to the origin. The potential V1 at P due to the charge Q1 can be written it as V1 is equals to 1 divided by 4 pi epsilon naught Q1 divided by R1p. Here R1p is the distance between Q1 and P. Then potential V2 at P due to the charge Q2 can be written as V2 is equals to 1 divided by 4 pi epsilon naught charge Q2 divided by position vector R2p, and by V3 1 divided by 4 pi epsilon naught Q3 divided by R3p, and so on. By superposition principle, the potential V at P due to the total charge configuration can be written it as sum of the potential due to the individual charges. Means total potential is equals to the sum of individual potentials. Therefore, the value of V1 is 1 divided by 4 pi epsilon naught Q1 divided by R1p plus value of V2 is 1 divided by 4 pi epsilon naught Q2 divided by R2p, so on up to 1 divided by 4 pi epsilon naught Q1 divided by Rnp. Here 1 divided by 4 pi epsilon naught is common. Just take outside, then inside the bracket it gives Q1 divided by R1p plus Q2 divided by R2p plus so on up to Qn divided by Rnp. Up to here, this is for 3 marks. And the potential outside the charged spherical shell, we can written as V is equals to 1 divided by 4 pi epsilon naught Q divided by small r. Here r is very much greater than the radius of the shell, capital R. Here Q is the total charge on the shell and small r is the distance of point from center of this shell, and capital R is the radius of the shell. Derivation of the relation between field and potential. This is also very important for 3 marks. Let us consider our two equipotential surfaces A and B. V and V plus delta V are the potential values. Here delta V is the change in potential, and delta L, which is the perpendicular distance of the surface A from P. When a unit positive charge 1 coulomb is moved along this perpendicular distance from the surface B to A against the electric field, then work done can be written as force into distance. Force can be written as Q into E into distance is delta L. Here value of Q equal to 1 coulomb, then value of W is equals to E into delta L. Taken it as equation 1. This work done is also equal to the product of the charge and the potential difference. That is W is equals to product of Q and the potential difference VA minus VB. Here value of Q equal to 1, VA is equals to V, VB is equals to V plus delta V. Then value of W is equals to 1 into V minus V plus delta V inside the bracket. Then value of W is equals to V minus delta V, which is equals to the value of delta V. Equation 2. Now compare equation 1 and 2, we know equation 1, W is equals to E into delta V. That is equation 1, W is equals to E into delta L. Equation 2, W is equals to minus delta V. Therefore, thus E into delta L, which is equals to minus delta V. Therefore, E is equals to minus delta V divided by delta L. Here, delta V is negative, so delta V can be written it as minus delta V. Then equation 3 becomes E is equals to minus of minus delta V divided by delta L. Therefore, E is equals to delta V divided by delta L. Here, electric field is in the direction in which potential decreases. The magnitude of electric field is given by the change in the magnitude of the potential per unit displacement normal to the equipotential surfaces at the point. This is the relation between electric field E and the potential V. Potential energy of a system of charges. Work done by an agency is assembling the charges at that position. Which completes the first part from the chapter Electrostatic Potential and Capacitance. In the next video, we can discuss some more derivations and some important topics from this same chapter. Those are derivation of expression for electric potential energy of a system of 2-point charges in the absence of external electric field. And next concept, potential energy in an external field, in which there are 3 cases: potential energy of a single charge, potential energy of a system of 2 charges in an external field, potential energy of a dipole in an external field. Difference between polar and non-polar molecules. And next concept, behavior of non-polar molecules in the presence of an external electric field, and behavior of a polar molecule in the presence of an external electric field.